Okay, so let's take a look at Zoltar Speaks. This is a lecture over how to predict the different types of chemical reactions. So how do we predict the products? Okay, in the previous lecture we learned how to predict the types. Now we're going to take that a little step further and try to figure out how to predict what types of products are going to form. The quote we have, the best way to predict the future is to create it. So we're going to look at some of these. The learning of goals, learning objectives that we want is that students will understand how to predict the products of the 5 basic types of chemical reactions. So basically we're talking about our single replacement, double replacement, synthesis, decomposition, and combustion. We want to be able to predict what the products are. So if we put these 2 compounds together, what are the products going to be? Number 2, students will understand how the activity series is related to chemical reactivity. So we're going to try to figure out what the activity series is and how is it related to how reactive something is. Number 3, students will be able to use the activity series to predict if single replacement or oxidation reduction reactions actually occur. So we're going to look at, well, do all reactions happen? Just because we put 2 things together, is it going to happen? So we're going to try to figure out how we can predict if a single replacement reaction will occur. And lastly, students will understand when solids will precipitate out of solution in a double replacement reaction, or a precipitate reaction. What we're looking at here is we're trying to figure out, well, does it produce that precipitate? Does it produce that solid? And how can we know if it's going to do that in advance? So let's dive right in. It says, how do you know what type of reaction you are working with? Well, the first thing we have to do is we have to figure out what type we have. The main thing here is what you start with is key. So our reactants, the reactants of a chemical reaction will determine what type of reaction will occur. So basically what we start with will determine what we're going to finish with and what type of reaction we're going to have. Okay, so it's all about what we're starting with because that's all we have. How do you know what type of reaction you are working with? So how do we figure it out? Well, if we start with an element and an element, more than likely what's going to happen is we're going to have a synthesis reaction. And the synthesis reaction produces a compound. So an element plus an element will produce some type of compound. Okay, that's for synthesis. Looking at this one, if we just start with a single compound, we can assume that it's going to be a decomposition reaction, and the product will equal 2 single elements. So if we start with a compound, just a compound, then what we're normally going to end up with is an element plus an element. Okay, great example is water, H2O. It breaks up into hydrogen gas plus oxygen gas. Okay. If we have an element plus a compound, we're going to have a single replacement reaction. Okay, and the product will be another element, another compound. Again, remember that like replaces like. So metals replace metals and nonmetals replace nonmetals. And lastly, if we have a compound plus a compound, then we are going to have a double replacement reaction. And remember, they switch partners and produce a compound plus another compound. Okay, and then we have our combustion reaction. If we have some type of molecule and oxygen, then what we're going to assume is that it's going to produce CO2. If that molecule happens to have a carbon in it, it'll produce CO2 plus H2O. Okay, so if we have a molecule plus hydrogen, we're going to produce a combustion reaction, which is CO2 plus H2O. Okay. After you know what type, how can you write the products? So once we know what type of reaction we're going to have, we have to write the products of what we're going to have. So you follow the rules for that type of reaction. So for a synthesis reaction, we have an element plus an element. It's going to produce a compound. Normally, it's going to be an ionic compound. So what do we have to do for ionics? We have to crisscross. Okay, all compounds must have a balanced charge, so we have to crisscross them out to make sure that they're balanced. And then we want to write the formulas and check elements for diatomic. And the normal place where people like to mess up is in those diatomic molecules. We forget about Brinkelhoff, and so they'll write bromine and they'll forget to add that 2, which changes the formula, changes the equation completely. So those are some things that we need to look out for. Follow rules for that type. What does it produce? Make sure that we crisscross for those ionic compounds, and when we write the formulas, and check the elements for diatomics. We always check for diatomics. So our first example, it says speculate on the products that could be produced when pure sodium, so we have pure sodium, which is Na, okay, is placed in pure water plus H2O. Okay, so when we're looking at this, we have an element plus right here we have water molecule, which it's more than an element put together. So what do you think is going to happen? Well, hydrogen has a unique property of having both metal characteristics and non-metal characteristics, meaning that in a molecule, it'll become ionized and it will give a lot of its electrons, give it one single electron to whatever it's bonded to, and it acts kind of like a metal. Well, here, remember, we always said when you look at water, think of water as H bonded to OH. So think of it this way. Well, sodium is going to come in and bump off that hydrogen. So I have hydrogen all by itself and then sodium bonded hydroxide. So hydrogen all by itself, we check, is it a part of Brinkelhoff? Remember, it's BRINCLHOF for the F, and then we see that yes, it is. It's right there. So instead of just writing hydrogen, we write H2. Okay. Plus now sodium, which is Na, is bonded to hydroxide, which is OH. It's an ionic compound. We need to crisscross. So sodium is going to have a positive 1 charge. Hydroxide is going to have that negative 1 charge. So we crisscross the 1s and we get NaOH. Okay. From here, we would go ahead and we would balance it out. Looking on at the next example, it says predict the possible products of the following chemical reaction. So we have potassium oxide plus our fluorine. So we have a compound plus fluorine, which is an element. Well, compound plus an element, we're going to have a single replacement reaction. So when we're looking at this, remember, like replaces like. So fluorine is a nonmetal. It's going to replace the nonmetal in potassium oxide. So that fluorine will replace that oxygen. So the oxygen's by itself. Is it a part of Brinkelhoff? Yes, it is. So it's O2 plus potassium, which is our K, is now bonded to our fluorine. Okay, so when we're looking at this, we check. We know that fluorine has a -1 oxidation number, and so does potassium. Switch spots, and we get KF for our potassium fluoride. Last example, it says predict the possible product for the chemical reaction. We have magnesium and oxygen, so an element plus an element. When we see that, synthesis. So it's magnesium bonded to oxygen in a compound. So anytime we bond this up, it's ionic. We need to crisscross, which magnesium is going to be our +2. Our oxygen is going to be our -2. So we crisscross the 2's, and they can be reduced down to, it's a 2-to-2 ratio. It can be reduced down to a 1-to-1 ratio, which is magnesium oxide. So let's start talking about the activity series. Now that we know how to predict the types of products in the types of reactions that we have, let's look specifically at the activity series and how it's used in single replacement reactions. Now, what is the activity series? The activity series is a list of metals with increasing reactivity. Basically what this means is that the most reactive is on the top of the list. So we see lithium's up here. It's on the very top. It's the most reactive metal. The least reactive metal will be on the bottom. So we see that gold is way down here. And so it's the least reactive metal. So the most is on the top, the least is on the bottom. And the way that it works is that when you have something that is on top, it likes to react more and will actually switch places with something that's below it. So How can the activity series help predict the chemical reaction? Remember, again, it's only for single replacement reactions. We don't use it for anything else. And if pure element is higher on the series, it will replace the cation in the compound. So if the element in a single replacement reaction, the element plus a compound, if the element is higher than whatever the cation is. So when we have the metal that's bonded in that compound, if it's higher up, the element, then the reaction occurs. If the single element, so the element is lower on the activity series, no reaction occurs. So if you're on top, say lithium, lithium can replace anything below it. Okay? But zinc can replace anything below it, but nothing above it. So if zinc is the single element, it cannot replace magnesium, aluminum, or manganese, aluminum, magnesium, sodium, calcium, barium, potassium, or lithium. Can't replace anything above it. Okay, so whatever by itself, if it's on top of the cation, the reaction happens. If not, then no reaction. So let's look at an example. So let's predict if the reaction between barium and zinc nitrate would occur. And if the reaction occurs, then predict the product of the reaction. So we have barium, which is Ba by itself. Is it a diatomic? No, it's not, so we don't put a 2. Okay, and then we have zinc nitrate, which we have zinc, which is +2, nitrate, NO3, -1, crisscross to make the compound. So we have Zn, NO3, 2. So there's our possible reaction that we have. So we're trying to look and see, will this reaction actually happen? When we look at it, barium, where is it? Barium is right, try to find it right there. Okay, and where's zinc? Zinc is way down here. So since barium is on top of zinc, okay, because we're looking at the metal, metals replace metals, non-metals replace non-metals, barium is on top of zinc, then the reaction occurs. So zinc is now by itself, and barium is now bonded to nitrate, which we have barium, which has a +2 charge, nitrate, which is NO3, -1, crisscross, and we get BaNO3, 2. Okay, that reaction actually happened. Let's look at the next one. It says predict the following equation, can it occur, and if it does occur, then predict the product of the reaction. So we write it out. We see that we have magnesium, which is just Mg by itself. It's not a diatomic, so we just leave it as Mg, plus our calcium, which is Ca, bonded to carbonate, which is CO3. Okay, this has a +2, -2. Since it's a 2-to-2 ratio, we crisscross the ones because they reduce. The 2 came down here, 2 came down there, but we reduce it down to CaCO3. So we look for it. Where is magnesium? Magnesium is right here. Okay, it can replace anything below it. Where's calcium? Well, calcium just tends to be above it. So since calcium is above magnesium, magnesium cannot replace calcium. So therefore, we would just say that no reaction. Looking at this one, predict if the following equation can possibly occur, and if the reaction does occur, then predict the product. So we have barium trying to replace iron. So we'll find barium. Barium is way up here. Can it replace iron? Which iron is going to be right there. It's below it. So since barium is on top, it replaces it. So iron is now by itself, plus barium is not bonded to nitrate. So we have barium +2, nitrate, NO3, -1, crisscross, and we get BaNO3, 2. And that reaction actually happened. So now let's start talking a little bit about solubility. Okay, what does the term solubility mean? Okay, when something When a substance becomes dissolved in another substance, like an ionic substance will dissolve and dissociate in water. So when something is actually dissolved, we say that it is soluble. When we put something as solid into water normally and it does not dissolve, we say that it's insoluble. So when we're looking at ionic compounds, normally ionic compounds will dissolve in water. We usually say that covalent compounds do not dissolve in water. So when ionic compounds dissolve, we say that they are in a dissociated. They dissociate in water. They break up into their ions. So when when we have not lithium, but sodium chloride. Say we have sodium chloride and we put it in water, just salt. We put salt in the water, it dissolves. So we say that it dissociates. So basically what you have is you have little sodiums, ions, and chlorine ions floating around in that water. They disassociate, they break up, and that is why they dissolve. And that's what we mean when we say that they are soluble. If they stay together, then we say that they're insoluble. So how do the solubility rules work? Soluble compounds stay in aqueous form. So basically, if something is soluble and we're looking at it, it stays in its aqueous form. It's soluble. We don't see anything floating in the liquid. When it's insoluble, it precipitates out into a solid and falls out of solution. So basically, something that's soluble, we say that we don't see anything floating in it. If it's insoluble, we kind of see stuff floating around in the water. Okay, famous quote, if you're not part of the solution, you're part of the precipitate. So that's what we mean, the precipitate. If you're not in the solution, then you precipitate out and you become that solid that sits on the bottom, that kind of floats around in there. Okay, what are the solubility rules? Now, the way we predict in a double replacement reaction if there's going to be a solute, or it's going to, not a solute, but there's going to be a precipitate. The way we do that is we look at the solubility rules, and these are on your star charts that you should have. And we see the solubility rules tell us what is soluble and what is insoluble. So here are just some rules. Everything on this top part, it's soluble compounds containing. So it could have anything, and we're really looking at the anion. What is it that metal bonded to? Because we're looking at these for ionic compounds. And basically, if it's bonded to one of those things, so if anything's bonded to nitrate or our chlorate or hyperchlorate, any of those guys, it's always going to be soluble. Okay, we can see that we do have some exceptions. So if it's an exception to being soluble, it then becomes insoluble. Okay, down here we see that we have some insoluble compounds. Those contain, and it has these anions right here. Okay, so anything bonded to this is going to be insoluble. That means it's going to form a precipitate. Okay, there are exceptions. If it's an exception to being insoluble, then therefore it is soluble. So let's look at the two that we have right here beside us. We say that lithium phosphate is soluble. Okay, so we look and we find, what is lithium bonded to? Well, it's phosphate. We find phosphate, it's right here. It's in the insoluble list, but there's an exception. Compounds containing ammonia and alkaline metal cations. So lithium is an alkaline metal, so it's an exception to being insoluble, so therefore it's now soluble. We have our calcium phosphate, which it says it's insoluble. Okay, there's phosphate, that's what it's bonded to. The exceptions are ammonia and alkaline metal cations. So this is an alkaline earth metal, so it's not ammonia, it's not the other exception, the alkaline metal, so therefore it is insoluble. So when we're looking at this, how can solubility rules help us predict double replacement reactions? What this boils down to is that if there's no precipitate, there is really no reaction. All ions are still in the dissociated form. So basically what this means is that if there's no precipitate that forms, we don't actually have a reaction. All they're doing is they're just kind of floating around in solution. They're floating around their dissociated forms, so what they break up into. So if there's no precipitate, Are they there? Yeah. Does anything happen? No, not really. It's not really a chemical reaction. Not a new product is being formed. Now, if there is a precipitate that forms, so that solid that falls out of solution, there has been a double replacement reaction, and that cation and the anion precipitate out of solution. We see that solid. So no precipitate, no reaction. If we see a precipitate, it's a double replacement reaction. So some examples. It says predict if a reaction between silver nitrate and zinc chloride would produce a precipitate. So we have silver nitrate. So we have to write out their formulas. Silver nitrate, we have Ag, and the nitrate is NO3. So silver is always +1, nitrate -1. We crisscross, and we get our AgNO3. Okay, that's our first compound. Then we have our zinc chloride. So our zinc bonded to our chlorine. Zinc is going to be +2, chlorine's -1. We crisscross and we get ZnCl2. Okay, when we're looking at this, we take this other compound up here, and basically what we're saying is that we're putting them together in an aqueous form. We're putting them together with water. So look, what's supposed to happen is a double replacement reaction. So silver is now going to be bonded to chlorine, which they both have +1 oxidation numbers. So what we'll see is we'll have AgCl +1 -1 crisscross, and we get our AgCl. So we look, if there's a solid, if this is insoluble, then we have something that precipitates out. So we look at it and we see that we have chlorine. There it is. That's what silver's bonded to right there. And then we see, are there any exceptions to it? Because it is soluble, so there shouldn't be a solid. But let's look at the exceptions. It says a compound of, we have our silver. So silver chloride, since chlorine's bonded to silver, this will be a solid. So that is a precipitate. The other thing that we could possibly have, let's see what zinc does. Zinc, which is +2, is bonded to nitrate, -1, crisscross, and we get ZnNO3, 2. That's our other compound. So those are the two that we have. What is it bonded to? It's bonded to nitrate. Look at nitrate. There it is. Does it have any exceptions? No. So this is aqueous. So that will stay in solution, and that silver chloride will fall out of solution. That is a solid, so therefore there's a precipitate. Double replacement reaction actually has occurred. Next example. We see that we have our calcium carbonate and ammonium chloride. So calcium carbonate, we have our CaCO3. Ca is +2, carbonate -2, crisscross, and we get our, since they're both 2 and 2 ratio is a 1:1, so CaCO3 plus our ammonium chloride. So ammonium, okay, we know what that is. It's polyatomic. It's NH4 with a +1 charge. Chlorine, -1, crisscross, and we get NH4Cl. Okay, what are the possible products that we could have? Okay, the possible products is calcium bonded and switches places, and it's now bonded to chlorine. So CaCl +2 -1 crisscross CaCl2. Okay. Plus the other possible product that we could have is we have our ammonia, which is NH4 plus, and then our carbonate CO3 -2 crisscross, and we get our, I'll zoom in right here, NH4 2CO3. So let's look at if a reaction is actually taking place. So in our first possible product, we see that it's bonded to chlorine. Calcium bonded to chlorine. Well, where's chlorine? Chlorine's right there. Okay, the only exceptions that it has, compounds containing silver, lead, or mercury. It's bonded to calcium, which is none of those. So this is going to be aqueous. Stays in solution. Okay, our next possible product, we see that we have carbonate. Well, where's carbonate? Carbonate's right here. The only exceptions that we have, it's insoluble, so therefore it would form a solid unless, well, we see that it's bonded to the compound of ammonia, so that would be aqueous as well. So therefore, no reaction has actually occurred on that example because they're both aqueous. They're both dissolved. Our last one that we see that we have our magnesium nitrate and our potassium, and that should be our hyperchlorate, okay, or perchlorate. So we see these. Let's write our possible products. Magnesium switches and now it's bonded to chlorate, plus 2 ClO4 -1 crisscross, and we get our MgClO4 2, plus the other possible product that we could have is now potassium. It's bonded to that nitrate, so K, which is +1, NO3, which is -1, crisscross, and we get KNO3. So let's look and see if a reaction has actually taken place. So our first one, magnesium perchlorate. So we find ClO4. There's no exception to it. It is soluble, so therefore it is aqueous. So that's not a solid. And we see that we have nitrate and nitrate right there, and none. So therefore that is aqueous as well. So therefore there's no reaction because there's no solid compound that's formed.